So before we talk about how we use spectroscopy in chemistry, it's a good idea to review some basics about the electromagnetic spectrum. So on the screen here, you see the electromagnetic spectrum. On the far left-hand side, we have high energy, high frequencies, and short wavelengths. And on the far right-hand side, we have low energy, or low frequency, or long wavelengths. And as a little bit of vocabulary review, we say that on the electromagnetic spectrum, when we shift to the left, we are blue shifting, going to higher energies. And when we shift to the right, we are going to red shift, going to lower energies, or longer wavelengths, or red wavelengths. So on the electromagnetic spectrum, for pretty much all but one of the types of frequencies you see on the screen, we can use them in analyzing compounds we make in the lab. The one wavelength on the screen that we don't use are the gamma rays. Gamma rays are so high energy, so high frequency, that if we actually tried to use those to analyze molecules we make in the lab, we would end up destroying the molecules in the process of trying to analyze them. But for all of the other frequencies in the electromagnetic spectrum, we have a use for them in analyzing compounds that we make in the lab. X-rays you may be familiar with. We use that in X-ray crystallography to get the three-dimensional structure of molecules and see where atoms are positioned relative to one another. In ultraviolet radiation, we use that to probe electronic transitions in molecules as electrons bounce between molecular orbitals. We'll learn more about that later. And when we do UV analysis, we often do it combined with visible radiation. Visible radiation is just redshifted or just below UV radiation, and they go hand in hand. And remember, the visible part of the electromagnetic spectrum is the only part of the electromagnetic spectrum that the human eye is tuned to. And so there's this very narrow region of the electromagnetic spectrum called the visible part, and that's where we have our Roy G. Biv for the colors of the rainbow to remember the orders of the colors or energies or frequencies. So when we do a UV vis experiment, again, we're looking at electronic transitions between molecular orbitals. Then just below the visible part of the electromagnetic spectrum, there is infrared radiation, and we use that for IR spectroscopy. Infrared radiation, we will learn, corresponds to a type of motion in molecules where covalent bonds are vibrating. The two types of vibrations we get with covalent bonds that we can measure with IR radiation are stretching vibrations and bending vibrations. More about that later. Then just below infrared radiation, we have microwave radiation. Microwave radiation is measuring molecular rotations, okay? And then finally, just below microwave radiation, we have the large part of the spectrum known as the radio wave part of the electromagnetic spectrum. Now, in every nucleus of every atom, there are protons. And if we have the right combination of protons and neutrons, what we are taking advantage of there is that these protons, which all have a +1 charge and are all spinning like tops, generate a magnetic moment. And it just happens to be, coincidentally, that radio wave frequencies are able to perturb that magnetic moment of the protons in the nucleus. And so as we perturb that motion, or that magnetic moment, we can measure something about what's going on in the nucleus of the atom. This is called nuclear magnetic resonance spectroscopy, also related to magnetic resonance imaging, which we'll learn more about later. Okay, so that is the radio wave region of the electromagnetic spectrum. Now, a couple things to remember about energies in electromagnetic radiation. If we look at the Planck-Einstein equation, it says that the energy of a photon, or the energy of electromagnetic radiation, is equal to Planck's constant times the frequency of that radiation. Now, we can also say, all right, we know that the speed of light, which remember is a constant in a vacuum, the speed of light is equal to the frequency times the wavelength. That's shown on the bottom left here. Now, if we rearrange that equation so that we're looking for frequency, we see that by rearranging that equation, frequency is equal to the speed of light, or v for velocity. Frequency is equal to the speed of light divided by the wavelength. Now if we take that and plug it back into the Planck-Einstein equation for frequency, what we come up with is that energy is also equal to Planck's constant times the speed of light divided by the wavelength. And we go through this exercise to remind ourselves that energy is directly proportional to frequency. So as frequency increases, energy increases. And it is inversely proportional to wavelength. So as the wavelength gets longer, the energy gets lower. As the wavelength gets shorter, the energy gets higher. Okay? Now, we can use, as I said, any part of the electromagnetic spectrum here except for the gamma rays to probe something about the structure of one of the molecules we make in lab. Now, an analogy that I really like to use both in teaching and in thinking about spectroscopic analysis, an analogy that I really like to use is that of music theory. And it starts with the word instrument. So in music we have instruments, and instruments play musical notes. Well, in the laboratory we have instruments, and those instruments play musical notes, although the type of note we were talking about is not a sound note, it's electromagnetic radiation. And that instrument is being used to probe something about the structure of the molecule. Now, everybody has some basic background in music. Maybe you play an instrument now, maybe you used to play an instrument. I grew up playing trombone. But even if you don't play an instrument, chances are you were exposed to those little inexpensive plastic recorders that they use in a lot of grade schools to teach the bare basics about music. And so in music, if you look at what's on the screen here, we have a piece of music, sheet music. Now, if you study music, you learn that, first of all, these aren't just marks on a piece of paper. Each of these little marks, or each of these little musical notes, has a meaning. It is telling you that each of these notes is a specific note. It's a specific sound. It's a specific frequency. And so the first thing we learn how to do is how to label the notes and give them names, A, B, B flat, etc., etc. Well, if you have really good pitch or perfect pitch, then you can actually go one step beyond that and say, when you see a note, not only do you know what its letter is, but you know what it sounds like. And so in doing spectroscopy in chemistry, it's an awful lot like learning how to read sheet music, where in spectroscopy we'll look at an IR spectrum or an NMR spectrum or a UV-Vis spectrum, and looking at that spectrum, we'll learn how to read it, like how we learn how to read sheet music, and we'll learn what the various notes or the various peaks are in our spectra, and we'll learn how to interpret that and figure out what is it telling us about the structure of the molecule. Now, as an example of how this might work, let's for instance take 3 tuning forks here. Now I'm telling you that these 3 tuning forks are different notes, E, A, and C, and if we had these tuning forks, each one of these tuning forks would correspond to a very specific note, a very specific frequency or energy. Now, is there an experiment we can design where we, let's say, have a series of tuning forks here on the screen, and I've rubbed out the letters on the tuning forks so you can't see what note, you can't see what frequency is associated with each of these tuning forks? Can we design an experiment where we can determine what the frequencies are for each of these tuning forks? And the answer is yes. Actually, we can design a pretty simple experiment. And the way we do that is we take a tuning fork, we mount it to a soundboard or a resonating chamber like this one. And the way to think about what this is doing is imagine an acoustic guitar. If you have an acoustic guitar, that resonating chamber behind the strings is what allows you to amplify the sound. If you didn't have that chamber back there acting as a sounding board, then when you strum an acoustic guitar, you wouldn't be able to hear the notes. Okay, so this is going to amplify the notes. And so what we can do is, if we know what the frequency is of the tuning fork, and we play the tuning fork, and we use the resonating chamber, and we aim it at the other tuning forks that have had their frequencies or their notes rubbed out, then what we can do is the following. We take individual tuning forks of known frequencies, we whack on them with a rubber mallet, we shine them at these other tuning forks. This experiment will go easier if I mount each of these tuning forks on a resonating chamber, so it's easier to pick up and to amplify the frequency of the note that I'm playing with the rubber mallet. Then what I'll notice is one and only one of these tuning forks will start to vibrate the most. And in physics, we have some basic concepts called constructive interference and destructive interference. Well, the tuning fork that has the most constructive interference with the note that I'm playing is the same note, okay? It has the most constructive interference. And so if I have a series of tuning forks of known frequency, and one by one I play them and shine them at these tuning forks of unknown frequency, then I can one by one figure out what each of the notes is on these tuning forks. And so that's what we do in chemistry when we use spectroscopy, except instead of using tuning forks and looking at musical notes, we use frequencies that correspond to something in the electromagnetic spectrum, from X-rays all the way down to radio waves, and we shine those notes on the molecules we're interested in or that we're making in the lab. And if the molecule resonates with the note that I'm using in my instrument, my chemistry instrument, if the molecule sings, if it vibrates, if it resonates and sings back to a detector or a recorder, then that is telling me that the note I am playing is matching a note, a frequency, an energy in the molecule that I'm trying to analyze. I also think that it's interesting that the first place I ever heard the word resonance was when I was learning how to play the trombone growing up. But we hear the word resonance all the time in chemistry. Resonating electrons, resonance delocalization, resonating frequencies. And if we think about what's going on in the molecules as standing waves, much like on a piano string or a guitar string, then it makes sense that we use the word resonance in music and resonance in chemistry. So my instrument in spectroscopy is simply playing a note, and I'm looking for that note to resonate with something in the molecule, and that will tell me something about the structure of the molecule. I then get pieces of a jigsaw puzzle, I put them all together, and eventually I come up with the entire structure of the molecule. Now we're going to look at these types of spectroscopic techniques one by one. And we're not going to look at all of these techniques. We're in organic chemistry, we're going to focus on 3 of them. We're going to focus on UV-vis spectroscopy, which again we'll learn talks about electronic transition of electrons between molecular orbitals. We will also learn about infrared radiation, which corresponds to covalent bonds either undergoing stretching vibrations or bending vibrations. And we will also look at radio wave electromagnetic radiation. And that is where we are looking at the magnetic properties of atomic nuclei being perturbed by radio waves. And we'll look at what information we can get about the structure of a molecule by perturbing the nuclei inside each atom in the molecule.